Okay, welcome to part 2 of lesson 4.3. I just looked at the timestamp of what I just filmed, and it was 50 minutes. So, dearest apologies on that, but I don't think I'm reshooting that. I think I'm just going to go straight into this one and try to be a little bit quicker in my explanations, okay? I know, I'm sorry, guys. I'm just so lethargic at home. I'm just enjoying talking about the math, of course, right? I was having a good time, right? Remember, you can always put those videos on double speed to help you out. Okay, so let's get started here. Part 2, we're continuing our, the sort of first part of this video is a review from Algebra 1 on simplifying radicals. So I'm going to explain what that is, show you how it's done, but this is more or less recap, and then some practice problems to model it. And then something called rationalizing a denominator, which is a skill you kind of need. It's a general algebra practice that we usually do in these classes, okay? So starting off, simplifying radicals. When we get to solving quadratics, right, solving quadratic equations, you're going to be, we're always kind of looking to make our answer as simple as possible. It's just good form. Yeah, that's how my pre-cal teacher said. He said, it's just, you just operate with good form. You know, you just want to make it simple and nice to read. And so part of this involves simplifying radicals. Now, this word radical, we use the word radical in math. It means this root symbol. So it could be square root, could be cube root, could be fourth root, right? Radical refers to this sign. So simplifying a radical essentially means reducing the complexity of the number inside that root. So like here you have square root of 24, right? Thing is, if we go back in the, way long ago, before we had calculators, we had to sort of compute square roots by hand. And if you had a really big number, like, I don't know, I'm just making something up. Like, let's say I had this, right? I wouldn't actually want to find that by hand. I might like to simplify how big that number is into something smaller. So maybe I've already calculated a smaller square root and then could just kind of use that in my calculations, yeah? So that's kind of why we do this, but it's also just general practice. And as I said, good form. Yes. Okay, so I'm going to show you two methods here in simplifying. Most people do prime factorization, but once you get really quick with it, and if you really know your times tables, the other method's better, okay? So prime factorization basically just means, hey, split it all up until you see all of its prime factors, and then you can find the perfect square pairs. What? Perfect square pairs, huh? So I say, look, and we're going to use, before I start with either of these methods, there is a rule about radicals we know. And that is that the square root of a times b, two numbers being multiplied underneath a radical, you can separate the radical like this, okay? It also means they combine. If you had these, you can combine them under the single root, okay? It's only for multiplication and not addition, and it's a property we're going to talk about in the spring. But we're not there yet. But just know for now, this is something you're allowed to do. So let's look at 24 and find its complete prime factorization. So we're going to take 24 and divide it into all of its prime factors. I say 2 goes into 24, makes it with 12, 2 and 6, 6 is 2 and 3. So what this means is the square root of 24 can be written as the square root of 2 times 2 times 2 times 3. And what we're going to look for here is pairs of the same number, and I'll explain why. The square root operation means what number times itself gets you that number, right? So when you say the square root of 4, we say that that's 2 because 2 times 2 is 4, right? That means if you take the square root of both sides, the square root of 2 times 2 is the square root of 4, right? So this property I said up here suggests that you can split up the multiplication into their own radicals. So you can split this up as 2 times 2 and 2 times 3, right? And so what we just said right here, the square root of 2 times 2 is the square root of 4, which we know to be 2. So you can just say, hey, square root of 2 times 2 is 2. But 2 times 3, there's no pairs there, right? Because if you're going to do square root of 9 as 3, then you would need 3 times 3 equals square root 9, right? But you don't have a pair. So, when you're doing simplifying radicals, you're looking for pairs because the pairs make perfect squares, which means you can take the square root and get an integer. So 2 root 3 does not simplify further. You can't take out any more perfect squares. So 2 times 3 is 6. And so this is what we consider a simplified version of the number, right? And I guess in sort of the old school utility of this, the old school utility is we don't want to calculate root 24 by hand, but we already have a book that tells us what square root of 6 is because we already did that one by hand earlier. So we just take that decimal and then we multiply it by 2 and we're done, okay? It's just kind of nice, yeah? Okay, method 2 is factoring perfect squares, and this is how I do it, really. Just think about perfect squares, 4, 9, 16, 25, 36. What are your perfect squares that go into a number? So 24, we just know from the perfect square list here that the number that goes into 24 is 4, and 4 times 6 makes 24. And looking at 6 and knowing its factorization, 6 is not, divisible by any of these perfect squares. So you can just say that the square root of 24, that's ugly, hideous, disgusting. The square root of 24 is the square root of 4 times 6. Of course, that you can separate that using the property of roots that says this. Square root of 4 is just 2. So this is then 2 root 6, as we got on right here. Yeah, same thing. Yeah, whatever. I don't really care how you do this, just that you can simplify. It's just a basic mechanic of algebra, okay? Another couple examples. Here's the square root of negative 450. So the way you could do this with method 1, by the way, notice the square root of a negative. Ooh, that's interesting. So we'll just break down 450. We don't really care that it's negative too much. 450, you can break that into 45 and 10. 45 is 9 and 5, and 3 and 3. 10 is 2 and 5. Beautiful. So that means the square root of 450 can be rewritten as the square root of the prime numbers, 2 times 3 times 3 times 5 times 5, right? Let me fix those 5s. Now, hold on. That's 450, but I want negative 450, so that means all of that is multiplied by a negative 1. Now, remember, looking for perfect square pairs, right? Perfect squares come in pairs. So 2 doesn't have no other 2s to pair with. 3s have a pair. 5s have a pair. And then you have this lonely square root negative 1. Now see, square root of 2, I don't know what that is, so it's the square root of 2. But square root of 3 times 3 is 9, right? Is square root of 9, so that comes out to 3. Square root of 5 times 5, that's square root of 25, that's just 5. And square root of negative 1 is what we define to be I, right? So put all of this together. You have 3 times 5. 3 times 5 makes 15. And then you have times the square root of 2. And it's imaginary because the negative, right? It's a square root of a negative. So we put this little I here to represent the imaginary unit, right? This is an imaginary number, 15 root 2 I. Okay? And again, it's just coming from finding those pairs that are there. And the only reason this problem is different is because you have the square root of negative 1, which you can separate and just call it I. Okay? To see the other method, it's really the same thing, but you just focus specifically on perfect squares. So 450 is, so 9 goes into 45 50 times. And 50 is 25 and 2. So you could say, okay, 450, is it negative, is negative, sorry, we'll save that, is 9 times 25 times 2 times negative 1. And so then now you know that that's square root 9, square root 25, square root 2, square root negative 1. And so you can say, okay, that's 3, 5, root 2 we don't know, and then root negative 1's I. So there it is again, 15, root 2, I. And you're done. Okay? Again, I don't care. It doesn't matter. This is just a basic mechanic of algebra you do. If you want to break it into its prime factors, yippee, go ahead. If you want to break it down purely into its perfect squares, hooray, go ahead. It doesn't matter. Okay? I might recommend, if this is your first time watching the video and you're not just reviewing from class, pause the video and try these. See if you can really get them. I will go over them very quickly, okay, without too much explanation here, because I think that was already enough explanation. Hopefully, I don't know, hopefully. Okay, so here's the answers. Square root negative 36. I said, well, that's just the square root of 36 times the square root of negative 1. And the square root of 36 is 6, and the square root of negative 1 is what we call I. And so the square root of negative 36 is 6i, and we are done. Hooray! We move on to square root 72. 72, I know this to be 9 times 8. 9's a perfect square. 8 is 4 times 2. So I like to say, okay, that's square root of 9 times 4 times 2. And I was just focusing on perfect squares there, right? Square root of 9, square root of 4, square root of 2. Square root of 9 is 3, square root of 4 is 2, square root of 2 is square root of 2. That means it's 3 times 2 is 6 times root 2. Done. Okay? Again, you can do the prime factorization method. It doesn't matter. Whatever you need to do, simplify. I'm showing you how I do it. Now, 294, that's a little tricky because I'm pretty sure 294 is a multiple of 7, but I don't know if that sticks out to everyone immediately. So here's 294, which is very clearly even. So we'll divide it by 2 and get 119 goes in, wait, what? No. 9. It goes in 4 times, and 14 is 7. Okay, so 14, 7. Okay, so 147, that's a 14, so that looks like it's divisible by 7. 7 goes in at 147 21 times, and 21 is 7 times 3. Okay, nice. So this is square root of 2 times 3 times 7 times 7. So the 2 and 3 are left alone, but you can pair the 7s together. And of course, square root 7 times 7, that's square root 49, which is 7. So it's root 6 times 7. But really, the way we write that is you put the rational number in front, and then you put the radical after. You put the irrational component right there. Okay? So I simplify that as 7 root 6. Yeah? Cool. Let's look at negative 192. 192. Also another number I'm not totally sure of, so I'll divide it by 2. And let's see, that goes in 90. Wait a minute. 2 times 9 is 18. Then it's 12. So 96 times. Okay. 96, let's do that by 3. Yeah, 3 goes to 3, that's 32. Oh, man, 32 is 2 and 16. Okay, I like that. So I'm going to stop there because 16 is a perfect square, okay? And so I'll say, okay, this is 2 times 2 times 3 times 16, and then times the negative 1, yeah? Well, I got a pair of 2s. I got square root of 3. I got a perfect square, 16, and I got the square root of negative 1. So square root of 2 times 2 is square root of 4, which is 2. I don't know what root 3 is. Square root of 16 is 4. And then I call square root of negative 1, I. So that's 2 times 4, which is 8 root 3, I. And we are done. Okay? There's so many different ways you could do this. I'm just trying to model a variety of ways you can kind of think about this, right? Of course, you can continue to split 16 all the way down like this. That's fine. But usually, I mean, if you find a perfect square, there's no reason in furthering factoring it because you can just pull it out anyway. Okay, negative 243. I'm a little lucky here because I know 243 is 3 to the power of 5. So that means it's 3 to the power of 4 times 3. And 3 to the power of 4 is 81 if you didn't know. So this comes out to 81 times 3 times a negative 1. But of course, the square root of 81... All right, so I'm separating these all. Square root of 81 is 9, then a root 3, and then root negative 1 is just called I. And you are done. Yeah? If you didn't see that, you could probably just divide this by 3 from the get-go, and then you would see that it's 81 if you didn't know your powers of 3. It's not essential to know that for that question, okay? So 9 root 3i. Okay? One more. 288. And you might say, oh, well, 288, you could divide that in half and get 144. Hey, 144, my favorite perfect square, right? Doesn't everyone... Look, comment below. Don't you love 144? That looks like a B. I want a little heart. Don't you love 144? Because it was the last times table thing you had to learn, 12 times 12, because you probably didn't go past 12 on the little table sheet or whatever you did in school. So you just love 140. It's just you never forgot it, right? Square root of 144, 12. And then there's a root 2. So you are done. Ta-da! And that is your Algebra 1 review of simplifying radicals. Hooray! Okay. Let's move on from this into some really, really new things, maybe. Okay. Second half of the lesson is called Rationalizing Denominators, okay? And let me just take a minute to explain the purpose of this, because some mathematicians have a gripe about this, and I think they need to hush, but I also get it. And so, okay. Something we do in Algebra 2, Pre-Cal, and Calculus classes is rationalize denominators. I say, what does that mean? I say, well, if you have an irrational expression in the denominator, here's an example, 1 over square root 2, right? Square root of 2 is like roughly 1.414, okay? And... traditionally, if you think like historical humans without calculators, right? To divide 1 by square root 2 means how many square root 2's fit into 1. Or in other words, how many 1.414s go into 1. But the thing is 1.414, this is a non-terminating decimal. It honestly keeps on going. So it's up to you to decide when to stop until whatever is accurate, right? And that's not that fun, yeah? Dividing by some sort of infinite decimal like this, it's not nice. It's a chore to actually carry out that division. It's much easier if you had like square root of 2 and you had to cut that in half, yeah? Because you could have 1.414, and all those decimals, and you could easily divide that by 2, right? Whereas dividing it by an infinite decimal, that's kind of, if you said like 2 divided by 1.414 infinitely, yeah, what? That's not fun, okay? So that's kind of why we do it. But the reason I said some mathematicians complain about it is, hey, guess what? We live in the modern era, 2024, or whenever you're watching this video. Calculators can compute the 1 over the square root of 2 with very quick precision and ease, right? So there's not really a use in doing this anymore. as far as technology allows us to go. But, in your mathematical careers of learning Algebra 2, Pre-Cal, and Calculus, it's kind of a useful technique. It just is. One, it's helpful in simplifying our answers, but two, it's just a good algebraic mechanic. It helps you simplify stuff, and it also lets you interact with other expressions kind of nicely, yeah? And so we still retain the practice even though our calculators can do that today, okay? Now, how do you make it so that if you are dividing by a rational expression that you don't? And I would say, well, it's going to invoke something called the conjugate, yeah? So if you multiply, okay, first of all, we have to introduce what is a conjugate. So, excuse me, a short yawn break, as I always do. My little yawns. It gets late. I always yawn like around 10. Also, I'm saying the word yawn. Am I making you yawn? Am I triggering a response from you? Isn't there research on that? Okay, sorry, I'm getting excited. What is a conjugate? I say the conjugate of here's an irrational expression, a plus root b. The irrational conjugate of a plus root b is a minus root b. That's it. It's very simple. Conjugate is a very important word, and it's a word we're going to develop over time. The more you learn about math, the more you see with conjugates, and you'll see how useful they are or interesting or where they pop up in math. For now, all it is basically flipping the sign of a binomial. So we'll also have the complex conjugate, right? So a complex number is a plus bi, and so its conjugate is a minus bi. That's it. You just flip the sign of the imaginary component. The real number doesn't change. And it's the same for irrational. You keep the rational the same, but the irrational, you flip the sign, okay? And this is called the conjugate. It's useful for some stuff, okay? So basic practice, what is the conjugate of 3 minus root 2? Well, then it would be 3 plus root 2. It would not be negative 3. It doesn't mean all the signs flip. It just means the sign on that one component flips. So it's 3 plus root 2. The conjugate of negative 2 plus 5i would be negative 2 minus 5i. I just flipped the sign on the imaginary component. The conjugate of root 3, well, that's like saying 0 plus root 3. So the conjugate of that is 0 minus root 3. Yeah, just negative root 3. Same thing for 4i. That's 0 plus 4i. So the conjugate of that is 0 minus 4i, making the conjugate negative 4i. And so that's it. That's the idea of the conjugate. Okay. So practice. It says simplify each expression by rationalizing the denominator. Okay? And so say, how are you going to do this? Well, a denominator, if you have an irrational or imaginary expression, you can make it real and rational by multiplying by the conjugate on top and bottom. Yeah? If you do this, it's done. It forces the denominator to be a real rational number. And we like that. Okay? Because it's easy to divide by rational numbers. And it looks nice. It looks simple. So here's an example. Here's 1 over square root 3, right? We want to multiply by the conjugate on top and bottom. So the conjugate of square root 3 is negative square root 3. And so I'm going to multiply by negative square root 3 on top and bottom. But something about these single value expressions, you see how it's negative on top and bottom? It's not really doing it. The negatives aren't really doing anything because a negative divided by a negative is a positive. So it's actually not really necessary to have those. You could just say, okay, take 1 over root 3 and multiply by root 3 on top and bottom. 1 times root 3 is root 3. When the bottom is root 3 times root 3, which is just root 3 times 3, which is just root 9, which is 3. So the bottom becomes 3. And you are done. Okay? Done. Boom. You got it. Okay? And that's it. That's all we mean by rationalizing the denominator. We don't want that square root in the bottom, but it's fine if we have it in the top. Okay? And again, this is because finding out how many square root 3's fit into 1, icky, bleh. But finding how many 3's find into square root 3, that's not as bad by hand. Okay? Okay, next one, 4 over 3i. So again, you'd multiply by the conjugate, which would be negative 3i over negative 3i. Though I want you to kind of keep in mind here, like really what's going on, what's going to make your denominator real. I say, well, negative over negative, that doesn't change the fact that the denominator is I. So I don't really need those. And in fact, the 3's really aren't doing anything either, right? 3i over 3i, I say, well, 3 over 3 is just 1, and that's not going to do anything to get rid of I, so I don't really need that either. So you could just multiply by I over I, and watch what happens. You get 4i on top, and then you get 3i squared on bottom. But what is I squared? I squared, we said earlier in the last video, was defined to be negative 1. So then that's 4i over 3 times negative 1, or maybe better written as negative 4/3 I. Yeah? I wouldn't say it's better written, just, I don't know, I like it. Negative 4/3 I. You could also write negative 4i over 3. This is totally acceptable, fine, no worries, okay? But I'm going to write it like that, negative 4/3 I, okay? By the way, even if you kept those 3's, this would have worked out, okay? If you kept the 3's here, you would have done 4 times 3i is 12i, and 3i times 3i would be 9i squared, and the 12 over 9 part would just simplify to 4 over 3 anyway, okay? So it's not a big deal. So a few more, right? 2 over root 6, you can multiply by the conjugate. But really, all you got to do is say, okay, let's multiply by square root 6 on top and bottom. Then the top is 2 square root 6, and the bottom is root 6 times itself. That's root 36, which is 6, and you're done. See, these are so nice. You do this a ton in pre-cal. So often. Oh my gosh, do you do this? You do this like a million times in pre-cal classes, okay? This is going to be a nice skill when you get to that class. Okay. You can see those 3 examples. The conjugate doesn't mean a whole lot, right? Here's where it really kicks in. 2 over 1 plus square root 2. So what is the conjugate of 1 plus square root 2? It's 1, oops, that's not a 1. 1 minus square root 2. So you're going to multiply by the conjugate on top and bottom. And watch what happens. So the top is easy. You just do basic distribution. 2 minus 2 root 2. Nothing to do there. Over, and I'm going to, maybe do the math over here. 1 plus root 2 times 1 minus root 2. Let's do distribution. 1 times 1 is 1. 1 times negative root 2 is negative root 2. Root 2 times 1 is plus root 2. And then root 2 times negative root 2 is negative 2, like this, right? It says, okay, so this is 1, and then these cancel. And then root 2 times root 2 is just root 4, which means it's just 1 minus the square root of 4. The square root of 4 is 2. So it's 1 minus 2, which is negative 1. So what happens to the denominator is it just becomes a negative 1 when you multiply by the conjugate on bottom, right? By the way, the reason we're doing it on top and bottom is because you don't want to change what this expression is, right? You don't want to change its value. So number over itself is a ratio of 1, right? Anyway, 2 minus, you're dividing by negative 1, so you just flip the signs on both. 2 becomes negative 2, and minus 2 becomes positive 2 root 2. And that's how we write that irrational number, okay? And now you don't have that irrational in the denominator. It's just, there it is. That's the number. A few more. Almost there. Let's do 5 over 3 minus I. So I say the conjugate of 3 minus I is 3 plus I. I don't want an equal sign. I want times. 3 plus I over 3 plus I. Okay? The numerator is 5 times 3 is 15, plus 5 times I is 5I. So what's the denominator? Well, I'm going to do that a little aside again, right? It's 3 minus I times 3 plus I, and you just distribute. 3 times 3 is 9, then a 3I, then a minus 3I, then a negative I squared. Those cancel, which, by the way, this is always going to happen, and you have 9 minus I squared, but I squared is negative 1. So that's 9 minus negative 1 is 9 plus 1 is 10. So the denominator becomes a rational number 10, okay? We might like to write this as a complex number. Like I said, a plus bi, this is a complex number where you separate the real from the imaginary, right? And so what I'm going to do with this addition is split it up. 15 tenths plus 5i over 10. Now, 15 over 10 just simplifies as 3 halves, and 5 over 10 simplifies as a half, and then you have that I next to it, yeah? And so we kind of like this, and this will be useful when you do work with complex numbers. Because you don't want to write an answer this way usually. You might like to have it expressed like this, because this is how we write our complex numbers. This is sort of the standard way to write them. Yeah? Cool. Last one, it says negative 1 over I cubed. So, I mean, you could multiply by I cubed, I guess, right? The conjugate of I cubed would just be negative I cubed, right? So it doesn't really matter. I just say, let's just do I cubed on top and bottom, huh? Let's just see what happens. So then it becomes negative 1 times I cubed. That's negative I cubed on top. And I cubed times I cubed is I to the 6th, right? I say, ooh, I to the 6th. Well, what is that? I to the 6th is, actually, we did it in the last video, right? Right here. I to the 6th is negative 1, because it's 2 more after I to the 4th. Oh my gosh. I to the 6th is negative 1, so you have negative I cubed over negative 1. Double negative makes positive, right? And so this becomes I cubed. Except, wait a minute, we know what I cubed is, right? It is negative I. And so that is my expression, negative I, yeah? Because you don't really want to leave it with powers of I. Because, like I said, every complex number could be written a plus bi. So you don't need I squared, I cubed, blah, blah, blah. You can always, if it has I to a power, you can always simplify that to a single I somehow, yeah? And that's it. It's done. There's negative I. Amazing. That's rationalizing the denominator, and I hope that was helpful with that. Okay. There's a last little bit of math history here at the bottom. You might like to pause. I love talking about this in class. And so as a sort of wrap up to this lesson, where are sort of complex numbers coming from? And gosh, I love talking about it. I don't want to extend the video too much, but there's this Italian mathematician named Cardano, yeah? And Cardano he's kind of the guy that gets most of the credit with introducing complex numbers. You see, so many people in math saw square root of negative, and then the second they saw this, they just nixed it. They just said, nope, that's not it. That's not an answer, not real, right? Doesn't exist. But Cardano said, hold on, maybe they do, Maybe square root of a negative is low-key valid, right? Let's say, it's low-key valid, right? I said, I don't know, maybe. Cardano was interested in finding the solution to cubics, x cubed. So you know how we have the quadratic formula, something we're going to solve in class in lesson 4.4? It's this thing, right? This is the quadratic formula, which solves any quadratic ax squared plus bx plus c. So what Cardano was doing was he wanted to find the solution to ax cubed plus bx squared plus cx plus d, right? If I gave you a general cubic like this, what formula, just like the quadratic formula, what formula would solve that cubic equation, right? So that's what he was doing. And the way he solved it was by taking a literal cube like this and sort of breaking it apart into different regions, I'm not going to go into the details of how he did that because it's cool, but it's complicated. But in doing that, he found that, he starts out with a real cube and he does some math and he gets the square root of negative. And if he stops, then he's at a dead end. But if he keeps going, he gets an answer. And he gets a real answer. And so what was interesting about this is Cardano had a physical cube who the only way you could find its side lengths were by acknowledging the square root of a negative number, meaning the problem was not solvable unless you treated the square root of negatives as legitimate. Still, he didn't think this was that useful. So he still, just like Descartes, he dismisses this as useless and not very important. But he was the first guy to look at a square root of a negative and say, hold on, I'm not just going to stop my problem and say that this isn't possible. I'm going to keep going. So he's kind of one of the first guys to do that. Eventually follows, I think it's his protege or someone who's a friend of his protege, a guy named Bombelli, who continues the work of Cardano and said that, that's what it says right there. Bombelli finds that there are real cubic equations that had real solutions, but the only way to find these results would be to acknowledge the use of imaginary numbers and accept them to be just as real and valid as real numbers, right? So I guess kind of what I said about Cardano, but Bombelli actually believed it, Cardano found the existence, he's like, nah, you kind of have to pretend it exists, but he didn't like it. Whereas Bombelli said, no, I like this. You have to acknowledge this breaks. You can find real solutions to real cubic equations if you accept imaginary numbers as valid and true. And so eventually, as we said in the last video, 200 years later, we start developing that field of complex analysis. We start really diving into it, and they're useful. So there it is, a little bit of math history for you. Okay. I hope this video wasn't terribly too long. I know these last two are a little lengthy, but I'm hoping that they're helping you out, that you're getting all the material, all your questions are being answered, that I'm not raising more questions. Okay. We did a good job. We're going to continue with lesson 4.4 some other time. Go ahead, have a good night or a good morning or a good afternoon. Whenever you're watching this, take care, and I'll see you in the next one.